Our first speaker this morning is Gaurav Kumar from IIT, uh, and he will speak on identities of sums of sales types. So please go ahead.
Hi everyone, I'm Gaurav Kumar. I'm a first year PhD student at IIT Gandhinagar, and this is my joint work with my PhD supervisor, Professor Atul Dikshit and Aviral Srivastava. So I'll be talking about on some identities of the sums of tails type. So throughout this presentation, the variable q I'll take it as mod q less than 1 for convergence purposes, and we'll use this Q Pokemon notation, where subscript 0 describes its value as 1, subscript n describes this n product of these n terms, and subscript infinity describes this particular limit. So Ramanujan's Lost Notebook uh, actually has several original concepts, which and one of which is what is known as sums of tails identities. So there were two identities that Ramanujan gave, one of which is this particular sum written at the bottom. So what these identities, why these are described as sums of tails? Because out of these Q products, it takes certain tails and take some of those tails. And you get this beautiful representation for these sums of tails, where this particular sum, if you can recall, is the generating function of divisor function, and this is sigma q function, which we'll see in the upcoming slides. Another identity of the similar kind is this particular one, where also recall that this minus q infinity is the generating function for partition into distinct parts. Similarly, in this sum of tails identity, 1 by q square infinity is the generating function of partition into odd parts. And we have similar structure in this identity also, where we have divisor function at q square and this sigma q function, where sigma q function is a famous function of Ramanujan only, which is defined as this particular q sum, q n plus 1 by 2 upon minus q sub n. Sigma q has some very nice properties, and it is very much studied. Q 1 upon 224, sigma q is a quantum modular form. Sigma q has close connections with arithmetic of q root 6. And there are many more properties which I have not mentioned here. And Zaghi in 1999 derived this following identity of the similar type. So it is also a sum of tails identity, where we are considering q infinity in the numerator only and taking tails of it and taking the sum. So we get this expression, where we also have this divisor function on the right hand side. Andrews, Urnos, and Ono also find similar identities in 2001, where we take this particular sum, where t and a we can choose arbitrarily. They got expression of for these kind of sum of tails identities, and this second kind is this a infinity upon b infinity upon c infinity upon q infinity. So where we can choose a, b, and c arbitrarily. And they also showed that these sum of tails identities can be used to obtain values of certain L functions at negative integers. Before proceeding to what we have studied, I'll also like to remind the definition of partition, which we see as is defined for a positive integer n, which is a non-increasing sequence of positive integers whose sum is n, and each positive integer forming the partition termed as a part of that partition. So for example, we have these 7 partitions of 5, and Pn we are denoting as the partition function of denote the number of partitions of n. So P of 5 is equal to 7. And for any particular partition, the rank is defined as the largest part minus the number of parts in that partition. For instance, the rank of the partition 4 plus 1 of 5 is 2, because the largest part is 4 and number of part is 2. So 4 minus 2 is 2. Uh, we are also familiar with this famous Rogers-Ramanujan identity. So for mod q less than 1, we have this sum side qn square upon mod q sub n, which is equal to this q product 1 upon q5 infinity can q4 q5 infinity. And we have seen the partition theoretic interpretation of the left hand side, in which we are partitioning into such partitions where the parts differ by at least 2. And that's why we call such partitions as Rogers-Ramanujan partitions, because they are generated by this sum side of this identity. So the sigma q that we have seen that comes on the right hand side of the sums of tails identities has also a partition theoretic interpretation, which is that excess number of partitions into distinct parts with even rank over those with odd rank. It is the generating function of such partitions, and it occurs as the error term in the right hand side of the sums of tails identities. Now the question that we saw is that, is there a corresponding sums of tails identity with the related to Rogers Ramanujan partition? Because in distinct sigma q was associated with distinct parts, or we can reframe it as the partitions into parts where parts differ by at least 1. So we tried for Rogers Ramanujan partitions, and we tried to see if there is a corresponding sigma type function associated, and we can get it as an error term in the sums of tails identity. So to be precise, we try to obtain an expression of this kind of sums of tails identity, where this product is the Rogers Ramanujan identities product on the right hand side. So we try to obtain a theorem for the part, like arbitrary b and d, and then we take them as like raise q as q raised to 5 and take b and d as q and q raised to 4. So we get this particular expression in which we for the sums of tails of this kind of identities, and we get divisor function on the right hand side, but we were not able to completely simplify this double sum and obtain sigma to q type function on the right hand side. We'll discuss what corollaries that we can obtain out of this particular theorem. So for b and d equal to q, we can recover the result of n rows, 2 rows, and o no, which is this particular sum. Taking b and q and b equal to q and d equal to 0, we also obtain a different representation for divisor functions generating function. And this particular identity implies this beautiful identity. So if you can see, we are taking all the distinct partitions of n as pi. And if we take this particular weight associated with every partition pi, where s pi is the smallest part of the partition, hash pi is the number of parts in the partition, and we take this particular thing as weight and sum up, then we get the generating function of the divisor, the number of divisors of n. In taking d equal to 0 and b equal to q and letting q as q square, we recover Ramanujan's sums of tails identity, although the proof is not very straightforward. So we also need some other q series results in order to get to this particular identity from our main generalization. So this theorem 2 is what one of the q series identity that we obtain to get this corollary. One other corollary we can say we got out of our main theorem is this particular result at the bottom. So in order to interpret this, let pi be a partition of n, where L is the largest part. So we define tau e sub e n and tau sub o n as the number of even and odd divisors of n. P1n actually counts such partitions where the largest part L is even all other parts are odd and distinct, and it does not contain L minus 1 as a part. And we attach minus 1 to the power hash sub o pi as this as the weight, where hash sub o pi is the number of odd parts. And similarly, we define P2n, where L is even, no parts allowed in the interval L by 2 to L minus 1. And we attach this particular weight, where hash pi is the total number of parts and lambda pi is the multiplicity of the largest part. So because of the main result, we were able to establish this particular relation between all these functions defined for any integer, any positive integer n, and we can express P1 as P1 of n as this particular finite sum of these other three functions. Another identity that we were able to obtain is this particular sum, where this particular Pokemons are in the numerator. And we were able to obtain this infinite series with this finite sum. If you see, this particular finite sum has uh, a symmetric uh, representation also. Like if you see in this particular representation, this B upon Q is in pairing as a Q Pokemon, whereas minus D upon Q has exponent n. And on here, right hand side, D upon Q is coming as in the Pokemon, and minus B upon Q is coming as an exponent. So these are two results that we were able to establish using our main theorem. We also make you like to, in order to show this symmetric finite identity at the bottom, we also used Andrews and Onufri's following identity, which is this particular double sum expressed as this Q product. So what, to give you some idea, what we did is we actually tried to get a generating function of this particular sum. So we added some parameter and take sum over j from 1 to infinity, and we were able to express it in Q products, and the Q product we obtain comes in symmetric in B and D. So we can reverse the entire process and obtain this as the generating function for this particular finite sum. And we also obtained this particular representation for this finite sum when B and D are equal. So B and D are equal means we have put B equal to D in the Pokemon also and in the exponent also. So I'll be concluding this talk, and I'll be saying that the original question that led us to the study of sums of tails identity, if there exists a sums of tails identity of this particular sum, was not answered in the exact manner that we expected. That on the right hand side, we were thinking of coming of like sigma 2q type function, where we have defined this particular function in a separate work. Sigma 2q is the analogous of sigma q function, where sigma 2q is the excess number of Rogers-Ramanujan partitions with even rank over those with odd rank. Recall that sigma q that appeared in sums of tails identities of Ramanujan was the excess number of distinct partitions with even rank over those with odd rank. So what we expected is the appearance of this particular function on the right hand side of this expression, which is still not, we couldn't figure out. So I'll give you some idea like what caused the problem and why we couldn't figure it out. Because Andrew's proof of those the Ramanujan sums of tails identities begins with by obtaining alternate representations for the left-hand sides of sums of tails. So you can see he uses like combinatorial techniques to express this left-hand side in terms of this particular sum, both for both. and we were able to like take analogous of that particular thing, and we commentarily obtained the left hand side for our identity, and which was this sum of this particular two term sum. And later on, what Andrews uses in his proof is Ramanujan's reciprocity theorem. And throughout the literature, we couldn't find any identity that we can use in order to transform our particular sums or our sigma 2q into completing the proof and appearance of sigma 2q on the right hand side of the sums of tails. So this raises a natural question: if there exists a corresponding reciprocity theorem, which is like still not discovered and could be used in order to transform that particular sum into sigma 2q. These are certain references that we have used. Thank you.
All right. Thank you, Gaurav. Are there questions? Mm-mm. All right. We're off to a good start this morning. Our next talk is at 8:30. Thank you, Gaurav. That was a good talk.
Yes. Thank you very much.
Thank you.
It looks like the Science Center is still logged into our meeting,
Yeah,
unless you're there.
I am here,
Oh, okay.
and I logged into the meeting so I could have it on the big screen.
Right.
But
Okay.
but the audio doesn't seem to connect this morning. So I'm also through my laptop. Modern solutions.
Yep.
So what was the count for how many people have registered for the conference this year?
I never count. I have no idea. Um, so for people who followed the instructions on the website and sent an email to the Gmail account for the conference,
Hmm.
I certainly have all of their emails and names and all of that.
Mm-hmm.
But um, you know, life is short and no reason not to keep it simple. So and since I don't have to reply to any funding agency, uh, I don't have to keep count of how many people. At various times we would have 40 or more people logged on to Zoom during the in-person sessions. Um, but I only know that by happenstance. I just happened to see somewhere a number that were logged on. And of course, they're not the same 40 people. So it's usually a couple of hundred people. Um, and the CUNY Zoom can handle 300 people at one time. But you never get everyone logged on at one time. So you never have to worry about overloading the system.
Yeah. For one of the talks on, I don't know, Monday or Tuesday, I counted 31 people in the room.
Yeah, we had no. There was a nice attendance in the room also.
Yeah.
So I mean, I really am nostalgic for the time when this technology did not exist. And if you went to the meeting, you went to the meeting, and you were there, and everyone was there. And um, but that's not the way it works. Actually, it is actually the way it works. So there was a very, very big meeting, for example, for Krishna Ladi's 70th birthday in Florida a couple of months ago.
Mm-hmm.
And that was basically a meeting where everyone showed up. There were one or two people who, for one reason or another, could not attend in person and gave a Zoom talk. But basically, I don't even know if the meeting was carried on Zoom or YouTube. But basically, everyone was there, so it was very nice. But on the other hand, you get broader participation and much better dissemination of your results if
Mm.
people in uh, wherever they are in the world can log on and see it. Um,
Mm-hmm.
or in principle, at least, if we ever figure out how to do it, go to YouTube and watch the talks later. But um, I looked at what Zoom saves on the Zoom, and I didn't open any of the videos, but there's basically one video for the day. That is, once you turn on the computer, um, even though you're starting and stopping, I think it's like one long video. So, but I will leave it to my technical experts in Michigan or somewhere. Some people are helping me with that
Oh,
to
okay.
figure out how to deal with the videos and the YouTube uploads. Uh, when when I ran the meeting completely from home and saved everything on my computer here, then I
Mm-hmm.
had a separate video for each talk, but it took me all if not hours to upload them individually to YouTube. I mean, that's really, um, I mean, it has the advantage that it gets done. It's easy to do, but it takes a lot of time. we're dealing with this saving to the cloud. Saves time, but it's much harder to do, I think. Anyway, it'll work out. But that's enough.
So who's
Almost
helping
time for our
you?
next talk. Maybe our next speaker should upload her slides
Okay, sir. A few minutes.
or his slides. Yes, his or her slides.
It's Vivekanand.
Wait a minute. Is my screen visible?
If I am on it, I guess so.
Okay.
Yes.
Okay. Is it visible now?
Restricted set edition in abelian groups.
Yeah. So can I start, sir?
So the schedule is for 8:30, so we should wait another 4 minutes.
Okay.
Because a lot of people have the schedule and they're maybe logging in right now.
Okay.
Where are you right now physically? Vivekanand? Am I pronouncing that close to?
Yeah. I am in my college IIT Bhilai in India.
Mm-hmm.
And at my hostel room. Hello.
Yeah, we hear you. Yes.
Hello.
I hear you.
Can you listen?
You're not hearing me?
Yeah. I am India IIT Bhilai Institute name IIT Bhilai. Indian Institute of Technology.
Yeah, we were just talking about that before the first talk. There's like about 20 of them, right?
Yes, sir. Can you repeat it?
Yeah, so we were talking about the Indian Institute of Technology beforehand. There's like 20 of them around the country.
Yeah.
Is that right?
Yeah.
And what's the population of India these days? It's a billion
Maybe.
plus, right?
Yeah, 1.5 maybe
Oh.
billion.
Maybe 20 isn't enough. And your position there, are you a postdoc or grad student or
Yes, sir.
tenured?
Hello.
Hello, yeah, I hear.
Can you repeat, sir? I did not listen.
Oh, I was just asking what your role is at the Indian Institute of Technology. If you're a professor or grad student.
Yeah, I am a PhD scholar.
Uh-huh.
PhD scholar.
Excellent. So at one of these IITs,
Yeah.
how many students would there be? Is it on the order of 2,000 or 3,000 or 20,000 or?
For different IITs, different. For my IIT is maybe 1,200.
Mm-hmm. Yeah.
And how many in mathematics?
Mathematics PhD, 20 students. other degree, MSc student, Master in Mathematics, 12, 15, something.
So your microphone gets a little bit garbled sometimes there at the end. I don't know, maybe if you're not close enough to it or.
Okay, okay.
Hello.
Yes?
Okay, is it fine? My voice is clear now?
Oh, that's much better. Yes.
Okay.
Yeah. And I think it's time for us to get started.
Okay, let me
So our next speaker is Vivekanand Goswami, speaking to us from India on restricted set edition. Please.
Hello everyone. Thank you for joining the meeting. The title of my talk is Restricted Set Addition in Abelian Groups. I am Vivekanand Goswami from IIT Bhilai. In this talk, I will present our joint research work with Dr. Rajkumar Mistry on restricted set addition in abelian groups. Here is the outline of my talk. I will begin with basic definitions, some background, and then I will state the main result. After that, I will introduce notations that we have used in the proof of main result. And finally, I will present the references that I have used in preparing these slides. Okay, for a positive integer h and a subset A of additive abelian group G, the h-fold subset is denoted like this, and it is collection of elements of G that can be written as a sum of h element of A, and elements not necessarily are distinct. So the restricted h-fold subset is denoted by h hat A, and it is collection of elements of G that can be written as a sum of h distinct element of A. So as the title of my talk suggests, that I will focus on the H hat A on abelian groups. So in 1964, Those and Helbron conjectures that for a subset A of finite cyclic group of prime order P, the cardinality of 2 hat A is greater than equal to minimum of P and 2 times cardinality A minus 3. And this conjecture was proved by Dai da Silva and Hamilton in 1994. They proved that Nk, if A is subset of P prime P, then cardinality minus S square plus 1. In 1992, when order abelian groups, before stating the result, let me introduce one more notation, that is chi hat GH. Chi hat GH is minimum integer M such that if cardinality of A is greater than equal to M, then H hat A is equal to Z. The result states that suppose that G is an abelian group of even order, at least 12. If if G is of the form Z2R or Z2R minus 1 cross Z4, and H is 3 or n by 2 minus 2, then chi hat GH is n by 2 plus 2. And in all other cases, we have chi hat GH is equal to n by 2 plus 1. This here order G2 is set of elements of order 2 in G, and for other remaining cases, it is H plus 2. Later in 1999, Gallardo, Gikos, and Foucault gave theorem 3 for 2 hat A in abelian for finite cyclic group of order n. The theorem states that let A is subset of Z and such that cardinality is strictly greater than n by 2 plus 1, then 2 hat A is Zn. So then in 2002, Gallardo and other co-authors proved the following result in for 3 hat A in finite cyclic group of odd order. For any alpha greater than, there exists n equal to n alpha such that for all n strictly greater than t is greater than equal to alpha, and then we have 3 hat A is equal to Zn. And they also give this theorem for both even or odd order finite cyclic groups. This theorem states that for any integer s greater than equal to 12, except n is equal to 15, and for any subset A of Zn such that cardinality is strictly greater than n by 2, then 3 hat A is equal to Zn. And in the same paper, they conjecture that there is a constant C such that for any odd integer n, and for any subset A of Zn such that cardinality is strictly greater than 2 by 5 n plus C, then 3 hat is equal to Zn. I live by proving the following result. And let G naught is collection. Let A be a subset of G such that Z and 120 cardinality of G naught equal to Z, or A is contained in a coset of n integer 5 subgroup of Z. Which, if we choose Z is equal to Zn, where n is odd, then it is easy to get this result, this conjecture. Okay. Then in 2019, for odd order cyclic group cyclic group for 4 hat A, the Cheng and we proved this result, this theorem 8. The theorem states that let n greater than equal to 11 be an odd positive integer for any alpha strictly alpha naught, which is given by this expression. There exists n is equal to alpha naught, which is equal to 54 by 985 q plus alpha minus 1, such that for all n strictly greater than this capital N and A subset of Zn, if cardinality A is greater than equal to alpha, and then we have 4 hat A is equal to Zn. And we generalizes this theorem for arbitrary h greater than equal to and in arbitrary abelian groups. So this is our main theorem. States that let h greater partitions of h, and let alpha h minus 2, hx minus 2.
Oh. Okay. So Vivekanand, I can see that you're still logged in, but we're not getting your slides.
Or your voice.
Or your voice, yeah.
So these are some numerical alpha h. Yeah. Hello.
You were gone there for a minute, but I see
Okay.
I see you now.
Okay. Is it
And
visible now?
now I see your screen.
Okay. You can see the slides. Hello.
I can't see them yet. There they are. Yes.
Hello.
Yes, I can see your slides now. Oh, not now.
Okay, wait a minute. Now can you see the slides?
Yes,
Hello.
yes. I can see a table of numbers.
So now,
Yes.
okay, from where I should proceed is
Yes, please.
hello.
Yeah, please. This is a
Hello.
good place to jump back in. Vivekanand.
Okay, did you hear this when I explained this page
You cut out
slide?
about midway
Hello.
through.
Hello.
Mm.
From
Yeah, so
where?
yeah, this is
Hello.
so explain this slide, please. Yes.
From where I have to continue? From this slide or the previous one
You
or the
were
next one?
midway. Yeah, no. This slide, theorem 9.
This. Okay. So uh, I will explain it one more time. So theorem 9 is the main theorem that we have generalizes this previous theorem 8. So theorem 9 states that let h greater than or equal to 4 be an integer and let ph denote the number of partitions of h. Let alpha h be the unique positive root of the polynomial 3h minus 2 x h minus 1 plus x minus 1. Then for any alpha strictly greater than alpha s, there exists image alpha, which is equal to maximum of this and this, such that for all n is a abelian group G of order n, and if cardinality A is strictly cardinality A is greater than or equal to alpha n, then h hat A is equal to Z. Moreover, the alpha h satisfy these properties. That is, alpha s belongs to 1 by 3 or 1 by 2, between 1 by 3 or 1 by 2, and alpha h is strictly greater than alpha h plus 1 for every h greater than or equal to 4, and limit h tends to infinity, alpha h is equal to 1 by 3. Hello.
Yes.
Hello.
Hello. Please continue.
Hello. Am I audible?
Yes.
Okay. These are some numerical values of mh alpha and alpha h. So here observe that the alpha has values of s tends to as increases, alpha h decreases to 0.33. Okay. So before going to the outline of the proofs, let me introduce you some notation that we will be using there. So a partition of a positive integer h is h tuple lambda 1, lambda 2, lambda s, such that, and their sum is equal to h. Small ps be the number of partitions of h. Then ps is equal to this set, obviously, that we have, the way we have defined, and the set ph is, we also give the order on this set. This is called colexicographic order and denoted by this symbol. And we say two elements d1, d2, dh is less than in this order e1, e2, eh, if and only if there exists k belongs to 1 to s, such that di is equal to ei for I is strictly greater than k, and dk is less than ek. So for example, here see that this is 1, 1, 1 belongs to ph. These one are h times 1, and this 0, 1, 1, 2 is less than this. If these two are same for some lambda i's, then we compare for, we move towards left and then compare the elements. Okay, so that obviously that cardinality of pH is this small pH, And we lambda I denote the ith element of this pH set. And for R belongs to 1 to H and H belongs to pH, let mu lambda R denotes the multiplicity of R in lambda. And if lambda is equal to lambda I, then we simply write mu IR in place of mu lambda R. And let we denote lambda I is equal to this lambda I1, lambda I2, and lambda IH. And for H greater than or equal to 4, we fix this lambda I naught is equal to 0, 0, or this partition 1, 1, 1, 3. Here 1 H minus 3 times. So this alpha H denote the S times Cartesian product of A. And for M belongs to G, we define Rm, the number of elements of AH, such that each components are different and their sum is equal to M. And corresponding to each lambda I in pH, we define RIM. The RIM is number of elements of this form. Here, the first lambda I1, these first lambda I1 components are same, and so on. And the sum of these denote lambda 1 is equal to minimum value J. And if we use this lambda for the and we can rewrite this RIM like this. So to give the outline of proof, to prove the main theorem, we proved some lemmas, and the first lemma is this lemma 10. So for M belongs to this lemma states the relations between Rm and RIM. So for M belongs to G, we have the following identity that Rm is equal to this, the Rm can be written as the sum of this RIM and these coefficients. So we prove this lemma, we prove this lemma 10 by using this lemma 11. So this lemma is a polynomial identity. So let me state this, that let x1, xk be variables for t greater than or equal to 1, let pt is equal to x1t plus up to xkt. For h greater than or equal to 0, the elementary symmetric polynomial is defined like this, that h is equal to 1 for if h is equal to 0, and this summation if h is between 1 to k, and 0 if h is distinctly greater than k. Then we have this identity that EH can be written like this in terms of these PIs. So we prove this. So the next lemma that will be used to prove the theorem. The next lemma is we prove this lemma use iterative theory. Let me introduce you some notations from character theory. Let G had to know the dual group of G, which consists of all characters chi from G to C cross. C cross is a multiplicative group of non-complex numbers. It is well known that the G hat is isomorphic to G, and for any G belongs to group C, it denotes as A G summation A belongs to A chi AG. Here chi A is corresponding to A in corresponding element in G hat to A in G. Okay, so by using character theory, we prove this bound on this SAG, that the modulus value of SAG is less than or equal to m by 3, where G is non-zero element of group G. Okay, so we prove this this bound using this lemma also. So this lemma states that this lemma is due to Gallardo, Glucose, and other co-authors. So the lemma states that let Z greater than or equal to 3 be an odd integer and x be a positive real number for any x bar x1 x b in Rd. Let p x bar is equal to summation j is equal to 1 to d xj exp 2 pi ij by d. Then maximum value of dx bar, maximum modulus value of dx bar in this domain that close 0 xd is equal to x by 2 sine pi by 2d. Hello, am I audible? Hello.
Yeah, hello.
Hello.
We're following. It's good.
Okay. Any question up to here? Any question? Anyone has? Okay, I'm proceeding. Okay, now I will give you the outline of the proof. The proof is we have shown this identity. So idea of proof is that we will show that Rm is strictly for every n belongs to G, then we have H hat is equal to Z. So for that, we need bound on R1M, R2M, and R3M, so on RIM. To prove a bound, to give a nice bound for R1M, if we use character theory and this identity from character theory that RM, so RM1M is can be written as this summation is 1M like this. So just doing some algebra here. So we get this bound, and then here to prove bound for R2 and other Ris, we use combinatorics. And under the given condition, we have given stated in the main result, we get this that Rm is strictly greater than 0, and in this way we show that H hat is equal to Z. So I will conclude my talk by showing these references that I have used in the preparation of these slides. If anyone has any question, you can ask me. So thank you everyone.
All right.
Hello.
Thank you.
Hello.
Yeah, hello. Hello. Thank you.
Yeah. Okay, thank you. So I think there is a question.
So if
Okay,
somebody
that
has
is
a
fine.
question, please unmute and speak up. Okay. So since we have a few minutes here, so Vivekanand, what would the
Yes.
ultimate theorem in this direction be? Like
What would be?
yeah, what would the ultimate theorem be for this work? Like if you could prove anything you wanted in this direction, like how far would it go?
I could not understand your question, sir. Can you explain it?
Could you go back to the main theorem?
Okay, I can. Yeah, this. Hello.
Yeah, I'm still seeing the outline of
Hello.
the.
Can you see this? Hello.
Yeah, seems to be stuck on the
Can you
outline of
see
the
my?
proof.
Can you see
Sorry.
my screen?
Uh, so I can see the outline of the proof slide,
Okay.
but I think that's not the slide that you're trying to show me.
Can you see the main result slide?
No.
I don't know why I'm opening this. Now.
No. Maybe to stop and restart the share.
Okay. Now. Hello.
Yeah, so it says you started screen sharing, but let's give it a second to sync.
Okay, okay.
Yeah, it just seems to be hung. Sorry, well,
Okay.
we made it through the talk at least, with the slides turning.
Hello.
Hmm. Yeah, so I'm not seeing any slides. Um,
Is my screen visible to you?
no, it isn't.
So you repeat your question? Maybe I could understand.
Yeah, so the question was just like asking for a general idea of like if you could push these results as far as you, what do you think the ultimate truth is here about? Uh, so your main
Oh,
result says that if A is big enough, then this H hat of A is the whole group, right?
yeah, 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 yeah.
What do you think is fundamentally this connection between the size of the set A and the properties of the group, right? So it's obviously
Okay,
depending on the size of the group, but what other parameters should be involved there? Like, like
okay, good.
what shape would the perfect theorem have?
Okay, what shape would be perfect theorem? So maybe some degenerate condition if you can remove. And here we have shown that the for this alpha h is decreases and the when h increases. But I think for h greater than equal to 4, this alpha h should be 1 by 3. If 3 divides, if n is odd and 3
Hmm.
divides that n. I think you understand what I said.
Yes, yes.
You
Yeah,
got it.
that's a good answer. And that's the kind of answer I was hoping for.
Okay. I said this alpha s depends on h for h greater than equal to 4. But I think it should not depend on h. It should be same for all h alpha s. This could be the if it's a Sarf theorem and complete theorem would be there, then this should be like this.
All right. Thank you very much. Uh, uh,
Okay.
I don't know,
Thank
do
you.
we
Thank you, sir.
uh,
Thank you.
applause online is always a little peculiar, but you have my applause. Thank you for the talk.
Thank you, sir. Thank you, everyone.
And our next talk starts in a few minutes. The Sándor Kiss from Budapest. Ah, there we are.
No, it's Simin Yu from Korea.
Oh, there we are.
Oh yeah, hi. Um, let me sure. Can you see my screen?
Yes.
Thank you. Um,
Multiplicative irreducibility of shifted multiplicative subgroups.
yep. 2 minutes left.
So Mel, are you here right now or?
Yes.
Yeah. So with the recordings, you're taking care of the recordings, or you want me to be doing that? Or
So if everything's being recorded to the cloud, then all you have to do this morning is just start recording at the beginning of the talk and end the recording at the end of the talk. And then do that for each talk, but always record it to the cloud. So and all of the recordings are on my computer or on my Zoom account. So you don't
Okay.
have to do anything at all.
Okay, but I will do the starting and stopping.
Yes, please.
Okay.
Yeah, yeah. And the last